Let's answer this past paper question from paper 3, AQA A Level Chemistry. This question is about pH curves, and this is about the titration of a weak acid, which is propanoic acid, with sodium hydroxide, which is a strong base. So the first question, propanoic acid is a weak acid. State the meaning of weak in this context. So we know that weak acids only partially dissociate in aqueous solution. So this is the meaning of a weak acid. So only partially dissociate in aqueous solution. Suggest why a student doing an experiment to produce this curve, the curve for the pH curve, would add the sodium hydroxide solution dropwise around the equivalent point. So equivalent point is basically the end point. You need to do this. So the equivalent point is the half point of this vertical line. And then, as you can see, there is a large change in the pH with a very small addition of sodium hydroxide. So you need to added really dropwise, and this is your answer. So there's a large change in the pH with the small addition of sodium hydroxide. Give an expression for Ka of propanoic acid. So this is the first part of this question. So let's give the expression of the Ka. So Ka is basically the concentration of the hydrogen ion times the concentration of the anion, propanate anion, so C2H5COO minus, over the concentration of the undissociated acid, so C2H5 COOH. So this is the expression of Ka. And then use this expression to show that pH equals pKa when half of the propanoic acid has reacted with sodium hydroxide. So when half of the propanoic acid react with sodium hydroxide, that means the anion that is formed, which is the C2H5COO minus, the concentration of this anion will equal the concentration of the undissociated acid. So that will equal C2H5COOH. The hydrogen ion concentration doesn't equal the concentration of the undissociated acid, just the anion, because it formed salt, because half of that converted into a salt already. That means that Ka, they will cancel out in this now in this expression, which means that the Ka will equal the hydrogen ion concentration. And we know that the pKa will equal minus log 10 of the Ka, which means now the Ka equals the hydrogen ion concentration, means that the pH will equal the pKa. Use the pH from figure 4 when half of the propanoic acid has reacted to calculate Ka at 296 and 98 Kelvin. So now we need to look at the hydrogen ion concentration, the pH at when half of the propanoic acid has been titrated. So let's look at the equivalent point first, and the equivalent point will be halfway through this vertical line. So this is almost 20. This is halfway. So there is 20 centimeter cubed of sodium hydroxide. So to neutralize or to so for half of the propanoic acid to react, we need 10 centimeter cubed. So this is the 10 centimeter cube. So what is the equivalent pH when we add 10 of centimeter cubed of sodium hydroxide? This is, you can see that's almost 4.5 dpH. That means that the pH, when half of the propanoic acid has reacted, will equal 4.5. Now, we know from the question above that the pKa will equal the pH, or Ka will equal the hydrogen ion concentration. So now we need to calculate Ka. So the Ka will equal the 10 to the minus 4.5, which is the hydrogen ion concentration at this pH. So when you calculate that, that will give you 3.16 times 10 to the minus 5. Of course, it's going to be mole decimeter to the minus 3. So 3.16 times 10 to the minus 5. When sodium hydroxide solution is added to aqueous propanoic acid, the solution formed act as a buffer when between 5 centimeter cubed and 15 centimeter cubed have been added. Explain why the pH stays approximately constant during this part of the experiment. So now it acts as a buffer. How does buffer act? When you add a base, the base will react with the hydrogen ion, and that will shift, according to Le Chatelier principle, that will shift the dissociation equilibrium towards the right to increase the concentration of the hydrogen ion or to regain the concentration of the hydrogen ion, so the pH remain almost constant. So your answer will be that the OH ion will react with the hydrogen ions, and that will shift the equilibrium. So the equilibrium for the dissociation will shift to the right, of course, to maintain hydrogen ion concentration constant. Methyl orange and universal indicators are not suitable indicators for the titration of solutions of propanoic acid and sodium hydroxide. We know that methyl orange is not the best indicator for when you titrate weak acid with a strong base. This is because the pH range when the color of the indicator change is different from the equivalent point for this titration. So why we can't use methyl orange? We cannot use methyl orange because it wouldn't change color at the equivalent point. It wouldn't change the color at the equivalent point. Actually, it will change the color before the equivalent point, so it's not a good one to use. You can say equivalent point or end point. Any of these would work. And why not the universal indicator? We know that we cannot use the universal indicators for titration because the universal indicators don't have a distinct color change at the pH. So for the universal indicator, that there is no distinct color change at the equivalent point.